and welcome to this lecture. In this lecture, we are going to look at sum of independent random variables. Okay, so how to describe the distribution of the sum of independent random variables, how to go about calculating it, what are the important salient points to remember. We'll only get started here. We'll keep looking at this more and more as we go along in this lectures and the next lecture also. Okay. So first, let's think about expected value and variance for sum of n random variables. There are n random variables. I'm not saying anything more about their distribution. They could be independent, they could be identical, I don't know. I'm just saying n random variables, x1, x2, xn. They have some joint distribution, they live in the same probability space. Okay, so there are n random variables, and I'm going to define their sum. Sum is easy to define, you just add up all of them. Okay, I'm going to call the sum as s equals x1 plus x2 till xn. Okay. So it turns out you don't have to say anything more before we can write down a simple equation for expected value. Expected value for the sum is equal to sum of the individual expected values, because expected value is a linear type operator. So it gets into the right hand side, you have expected value of x1 plus x2 and it distributes inside the summation. Okay, so that's always true. So expected value of x1 plus expected value of x2 plus so on till expected value of xn. It's easy enough. Okay. So it turns out if you put this additional condition that x1 to xn are pairwise uncorrelated. Okay, what is uncorrelated? I've described it here. Expected value of xi xj should factor as expected value of xi times expected value of xj. If that were to happen, then variance of the sum is also going to become sum of the variances. Variance of x1 plus variance of xn. Okay, so let me write down so for the first statement, I'm not going to write down a proof, it's easy enough. I'll write down a proof for the second statement. So it's got to do with, s minus expected value of s, the whole square, isn't it? This is the variance of s. It's expected value of this guy. So let's see how to write what's inside this guy. Okay. So that is x1 minus expected value of x1 plus x2 minus expected value of x2 plus so on till xn minus expected value of xn. If you are the type who's getting quite upset with these lengthy sort of derivations, you don't like these derivations, you don't have to pay attention too much to the derivation. The final result is what's most important. I'm just doing this so that people who are interested in this can benefit out of it. Okay. So when you square a bunch of sums like this, you will have two types of expression. One type of expression will be, you will get all these guys, x1 minus expected value of x1 squared plus x2, each of them will get squared, and then you will get these cross terms, right? So you can write it down and multiply. You might have done this before in your life. And then you will get cross terms of this nature, x1 minus, so in fact you will get two of them, times x2 minus expected value of x2, so on. Okay, so I'm not going to write down all the cross terms. So an arbitrary cross term will look like this, right? So x1 xi minus expected value of xi times xj minus expected value of xj. So it turns out the expected value of this guy is actually equal to 0 if this is true. Okay, so this is something that I'm not going to do in detail. You can check it out. It's just you have to multiply this and then distribute the expected value over each term, and you use this formula. You'll see, everything will cancel. You'll get 0. Okay, so this is a crucial part. So all the cross terms vanish when you take expected value. Only the square terms will remain. And what is the expected value of the first term here? Expected value of x1 minus expected value of x1 whole squared. This is the variance of x1. Okay. So this is the crucial result. Pairwise uncorrelated. The expected value of the product xi xj has to be equal to expected value of xi, expected value of xj. And then variance of the sum is sum of the variance. Okay. So this is the result in words. This result is much more important. Sum of n random variables, mean of the sum is always equal to sum of means. You don't need any other condition. Of course, you need some existence conditions, but assuming those are true, this is always true. If uncorrelated, the word uncorrelated will be used loosely here, I should say pairwise uncorrelated. Variance of sum is also the sum of the variances. Okay, so it's a good fact to remember. Okay, so very good fact to remember. This pairwise uncorrelation, being uncorrelated, can be checked quite often using data. It's at least roughly, you can check that. It's not too bad. So it's a very nice fact to remember. Okay, so this is quite a powerful fact about expected value and variance of sum of n random variables. Okay, so in particular, if it turns out x1, xn are independent, okay, then they are of course pairwise uncorrelated. Okay, so if you look at our IID sample situation, our random variables are independent. When they are independent, they are also uncorrelated. So this above result holds. So independence implies uncorrelated, but uncorrelated may not imply independence. If you remember, I've showed you some example of this long ago. You may have a vague memory of it, but that's important to know. So independent is good. Independent also means variance of sum is sum of variances. Okay, simple result. Hopefully the result is clear, even if the proof was a little bit long-winded, involved calculations. Okay, there's a few extensions, simple extensions, but these are useful when you'll see. I mean, this is quick derivations of what results we saw before about sample variance. You can scale and sum instead of just summing. Right? Each x1 you can multiply by a1, and xn you can multiply by an. So this is like a linear combination of these n random variables. Ai are constants. Again, if you take expected value, this expected value goes in for any x1 to xn that would happen, and variance would sum like this if pairwise uncorrelated. Okay, so this is very important. So I'm assuming pairwise uncorrelated. So if that is true, this would happen. Okay, let me add it here also. Okay, so now let's push it a little bit more. This is a general result, and then now we're going to say IID samples. We're going to look at IID samples. So x1 to xn are distributed like x, and they are independent. Okay, identical and independent. Now if I do a linear combination a1 x1 plus an xn, if I do expected value of xn, what do I know about expected value of x1, expected value of xn? Each of them, they are all identical to x in distribution, so which means their expected value is the same as expected value of x. So you can take expected value of x common outside, you would get a1 plus a2 till an. Same thing would happen with a1 squared plus a2 squared plus an squared for the variance. Okay, so variance is going to be constant, they are independent, right? So of course it's uncorrelated, so all of these results are true. Okay. So now let's look at the sample mean. Okay, so x1 to xn is distributed according to x IID. This is the IID samples model, and we're defining the sample mean. Remember, sample mean x bar is a random variable. It's x1 plus x2, capital X1 plus capital X2 plus capital Xn divided by n, and this is nothing but a linear combination with each ai being equal to 1 by n. You just substitute that here. You will see expected value of, oh my god, this thing became a bit messed up, so apologies for that. Expected value of x bar is actually expected value of x, and variance of x bar is variance of x divided by n, right? So this n squared added up n times, you get 1 by n as the factor. So this is the result we saw before. I'm just reiterating that. Okay, so that's something it's important. So you see, simple extension of the previous result, we get the mean and variance of the sample mean. Okay, now we're going to start looking at sample mean versus distribution mean. We already seen that expected value of sample mean is equal to the distributed mean. Okay, we've seen that expected value is the same as the distribution mean. The variance is the same as is sigma squared by n. Okay, so as n increases, the expected value remains the same. It's always mu, but the variance is going to start shrinking. Okay, as n increases, the variance is shrinking, which means what? You're around mu, and your values, the values that you take are getting lesser and lesser and lesser spread. Okay, again, up to this it's okay. If all you wanted to say was that, it's okay, it's a fair statement, correct statement. Can we put some number to this? Okay, can we say how close x bar and mu are going to be? Okay. So maybe I want to put some number to it, right? So only when I say something about probability, I can say something a little bit better than saying, variance is going to 0, so distribution mean is going to be close to sample mean, but how much, right? It's a very natural question. You have to quantify it. How do you go about quantifying how close you expect x bar and mu to be as a function of n, as a function of other distribution parameters? Okay, important question, isn't it? Let's try and answer that. So you may ask questions like this. Okay, so remember, x bar is a random variable. It's not a constant. It's not one number. It's a random variable. The first time you get your samples, you may get one value for x bar. The second time you get your samples, even though it's from the same distribution, you can get a different value for x bar, right? In your samples, it's a different sampling, so you may get a different x bar. So different times you get samplings, you may get different value of x bar. The mu is the same. Okay, so the question you have to ask is, over very large number of samplings, how likely are you to be away from mu by some delta? Okay, so again, this is a probabilistic question because x bar is a random variable. Okay, a lot of people start thinking that sample mean is fixed, but remember, we are changing the samples. As you change the samples, different samples will give you different sample means. You repeat your experiment. You've seen this in your Monte Carlo simulations when you do them in Python, right? You repeat the same experiment, you get different numbers. Okay, so the numbers do end up changing. So only statement you can reasonably make is about probabilities. What is the probability that x bar, the sample mean random variable, is going to be greater than mu plus delta? Delta is the difference. Okay, so some difference that I have in mind could be 0.1, 0.2, 1, 10, or it depends on how large mu is. What is the probability that my sample mean is going to be greater than mu plus delta? Similarly, I can ask, what is the probability my sample mean is less than mu minus delta? Both of these I can combine and then ask this question, what's the probability that the absolute value of x bar minus mu is greater than delta? Okay, so this particular one, if you were to think of mu being here, this is mu plus delta, so mu minus delta, and if x minus mu, this is the region that absolute value of x bar minus mu is greater than delta. Okay, so that's a simple pictorial illustration of what happens. So I want to be able to say something about the probability of this. Okay, so of course, if you know the distribution of x bar exactly, or the distribution of x exactly, you can write down precise answers for this. Okay, you can define this event, you can find all the values of x1 to xn that will satisfy this event, find their probability, etc. But that's usually pointless. You may not know the distribution. First of all, the distribution may be so complicated, you don't want to find the distribution of the sum of these things divided by n. It's messy, very messy. Okay, so what we will settle for usually are good bounds. Okay, I say good bounds. Bounds itself is great, but good bounds are even greater. So can we get some good bounds, cheap and quick and dirty, simple bounds that will give us a sense of how large these numbers are? So I'm going to show you one such bound and one nice result, very popular result that comes because of it. Okay, so this result is called the weak law of large numbers. Okay, sounds nice. No, it's a fancy name. I really like that name. The weak law of large numbers. This is a law of large numbers. Okay, so in the long run, eventually something happens, right? So that's sort of like this law, weak law of large numbers. Okay, so here's the setting: x1 to xn is IID according to x, one distribution. Those are the distribution means, mu and sigma squared. Mu is expected value of x, sigma squared is the variance of x, distribution mean, distribution variance. Okay, now from the samples, you will get a sample mean x bar. Okay, and the expected value of x bar is mu, I know that. The variance of x bar is sigma squared by n, I know that also. All of these things we know. These are not the law of large numbers. This is the law of large numbers. Okay, so probability that x bar minus mu is greater than delta is less than or equal to sigma squared by n delta squared. Okay, so this is very simple use of Chebyshev's inequality. What is Chebyshev's inequality? Chebyshev's inequality says probability of x minus mu squared greater than delta squared for that matter, yeah, is less than or equal to expected value. This is actually Markov, right? Same as Markov, Chebyshev, they're all sort of similar, divided by delta squared, right? So that's all. This is a simple use of that. So these two are equivalent, right? Absolute value of x bar minus mu is greater than delta is, we'll put the x bar probability of x bar minus mu whole square is greater than delta squared, right? These two are the same. Now you just use Markov, Markov's inequality. This is positive random variable is greater than delta square is less than expected value of that random variable divided by delta squared, and that is nothing but sigma squared by n delta squared. Okay, so very easy application, and you get a bound. Notice how powerful this bound is. I mean, long back when we looked at Markov inequality, Chebyshev inequality, you might have said, oh, this bound looks bad, it's not very good, etc., etc. Look at how powerful it is. I don't know anything about the distribution of x. X could be anything. All I know is the mu and the sigma squared, and look at the powerful result I get. In particular, look at this n that comes up here. So for any fixed delta, as n tends to infinity, this tends to 0. Okay, delta could be anything you like. Delta could be 0.001 or 0.000001. Okay, I can always go to a n very large, so that this thing will swallow how much ever this 1 by delta square is and make it 0. Okay, sigma square of course needs to be finite for this particular proof. You will get it. Okay, so that is the result that's meaningful here. Notice this. Suppose I have a particular mu, x bar minus mu, probability that absolute value of x bar minus mu exceeds, let's say, delta. Delta is very small, think of it as 10 power minus 6. It's less than or equal to sigma squared by n into 10 power minus 12. Okay, so if n becomes 10 power 20, okay, then this is going to go to 10 power minus 8 and go to 0. So the point is, it's sort of like, I mean, don't think of delta being so small. Maybe delta is 0.1, right? So if delta is 0.1, and sigma squared by, even 1000 times 0.1 ends up being very small. Okay, so this quantifies the probability that the sample mean can deviate from the actual distribution mean. Okay, simple application. There are sharper inequalities than this, but this inequality itself is quite useful. Okay. Another reading of this inequality is, with probability more than 1 minus sigma squared by n delta squared, the sample mean lies inside mu minus delta, mu plus delta. Okay, probability that it's outside is upper bounded by sigma squared by n delta squared. So probability that it's inside is lower bounded, it's greater than or equal to 1 minus that sigma squared by n delta squared. So this is another way in which people write this down. Okay, so what is the meaning of this probability? So this is a question that is often asked. I will, maybe when I illustrate it, I will talk about the meaning of this probability. What is the meaning, in the sense, I mean, in what probability space does this, is this probability valid? Okay, so that's the question. So we will ponder on this question as we go along. Okay, but remember this question. I'm not going to answer this question immediately. You may be able to interpret it based on what I've described, but later on, when we actually calculate these probabilities in statistical problems, I will come back and keep asking this question. What is the meaning of this probability? And we'll debate it at that point. So one thing about Chebyshev inequality and Markov inequality, usually it provides a weak bound. Today, in the theory of sums of random variables, in particular this type of convergence results, there are very strong results. There are exponential results of different types. So you can sharpen this inequality. Don't worry about why this inequality comes. The most important thing about this inequality is it tends to 0. That much at least I know. Okay, how quickly it tends to 0, maybe it can be speeded up, but it does tend to 0. Okay, so the weak law of large numbers is often written as x bar converges to mu. People will use this word in probability. Okay, so these are all technical terms. Converges in probability. In this course, we're not going to go into detail of these things, but just remember this. This is just hopefully you understand what it means. So a result like this, if you can show the probability that something deviates, a random variable deviates from some value greater than even something very small can be driven to 0, then usually people say that random variable converges in probability. Okay, that's just a technical definition. It's not so important for us in this course. If at all you do advanced probability courses, these kind of results will come in. Okay, so this is weak law of large numbers. The way one can think of the law of large numbers is eventually if you observe something for a long time, the average that you see will be the distribution average. So it's like, you know, what justifies many things about law of averages, right? Nobody is going to be much better than their own average at doing something. Okay, so that's the law of averages. Okay, if you exceeded your average quite often, turns out bad days are ahead, right? So that's the law of averages or weak law of large numbers. Okay, so here are some examples. So let's look at some examples. In every case here, the distribution is known. Okay, n IID samples, I give you the distribution. Okay, you just plug in the formula and then say what the law of large numbers is saying. Okay, based on the Chebyshev inequality application, right? Chebyshev inequality needs the variance. The variance alone you have to calculate for the distribution. First is Bernoulli P samples. The variance is just P into 1 minus P. So probability more than 1 minus P into 1 minus P by n delta squared. Sample mean lies in P minus delta, P plus delta. Here is a uniform discrete distribution minus m comma all the way till plus m. The mean is 0. Variance is sigma squared. So that's the thing. Mean is P. Sigma squared is P into 1 minus P. Okay, the distribution mean. So here again, mean is 0 and variance is m times m plus 1 by 3. Okay, so this is a calculation. I'll let you verify this, the sigma square calculation. Here again, mean is 0 and variance is sigma squared, normal distribution with probability more than 1 minus sigma squared by n delta square. Sample mean lies in minus delta delta. So you can see how I'm using it, right? The mu comes here, mu is 0 here, so it becomes just minus delta delta. Okay, mu is p here, so it becomes p minus delta, p plus delta, and the actual sigma squared comes from the distribution. Uniform minus AA, this is a continuous distribution, and mu is 0 and sigma squared is a squared by 3. Okay, so that's the formula. So you just plug it in, you get the answers, right? So distribution is known. Remember, distribution is known. So when the distribution is known, you can make a precise statement about your confidence. The bound can be improved to make your confidence more precise, but you know the precision is okay to whatever extent we are able to precisely say about where I expect my sample mean to be. Okay, my sample mean is with some confidence expected to be within some delta of the actual distribution mean. Okay, when the distribution is known, this is very nice. Okay, let's look at this data case. We had the IRIS and the Taj Mahal and the IPL, right? 3 different cases we saw just a couple of lectures ago or so. So let's look at the IRIS data and the sepal length. We had 50 instances. The sample mean ended up being around 5. Sample variance is 0.1242. So we can say with probability more than 1 minus sigma squared by 50 delta square, sample mean lies in mu minus delta, mu plus delta. But what are we assuming when we say that? We are assuming IID samples model. These irises, the data that came, follows some sort of an IID distribution. And this seems to work if delta is greater than sigma by root 50, right? So this is sort of, I mean, if delta were to be lesser than sigma by root 50, probability this will go like, you know, negative. So if it goes negative, probability is greater than 0 is the only thing you can say, but that anybody can say, right? So you don't want that to go negative. So sigma by root 50 is sort of like the delta that you can tolerate when you look at sepal length. So it's okay. So maybe, I mean, I don't know the real sigma. That's the other problem, right? What is sigma? What do we use for sigma? I don't know the model. I don't know sigma. Maybe one can simply substitute the sample variance for sigma squared, right? You don't know it, maybe it's sigma squared sample variance, you put it in, you get something, right? So this it may not be too bad. Okay, so that's that. Okay, Okay, so the next thing about the Taj Mahal air quality, supposing you take PM 2.5, we have only 11 data points and the sample mean is 65.72, sample variance is 15.9 squared with probability more than 1 minus sigma squared by 11 delta squared. Sample mean lies in mu minus delta. Mu plus delta is all that we are able to say, and it seems to work for delta greater than sigma by 11. Root 11, I've just used it. Root 11 is something like 3 point something, and sigma is maybe around 15 based on what the sample variance is. So 15 by 3, you're already looking at a delta of 5, right? So you're going to be off, the best you can do is around 5, and it looks so shaky, right? I mean 11, so you see why 11 is a problem, okay? 50 was better, 11 is a serious issue. So when the sample variance 15.9, you expect sigma to be around 15.9, you're dividing by root 11, which is 3 point something, you're looking at a delta of at least 5, okay? So and even if you do that, your probability is like really small. The confidence you get is very small. So you have to go to a really large delta before you can make this probability very small. So supposing I want to make this probability 0.95, right? So I want this so supposing let me just do this calculation for you, okay? Supposing 1 minus sigma squared by 11 delta squared has to be greater than 0.95. So this is more than 95% confidence that you will be within that delta region, right? So this implies move to this side, move to that side, 0.05 by into 11 divided by sigma squared has to be greater than so let me just write it down a little bit differently. This would mean that delta squared is greater than sigma squared by 11 into 0.05. Okay, 0.05 is already 1 by 0.05 is what, 20. So which is the same as delta squared is greater than 20 by 11. So roughly about 20 sigma squared by 11, or delta is greater than square root of 20 by 11 into sigma. Okay, so notice that the delta value that you need is becoming greater than like root 2 by times sigma, 1.4 times sigma. Okay, you're not going to, this is just for 0.05 confidence. So you need a really large delta before you're able to say something, right? So it's a multiple function of the sigma. So it's not very nice. So sigma would be, I don't know if you can say 15.9 or something. It's already like 20, 25. So you can only put your sample mean within a window of 20 or 25. So your sample mean, distribution mean can be as low as 40, 45 all the way up to 80, 85 or so. So it's a wide window before you can say anything about some sort of a confidence level in this data, of course assuming IID samples and all that. Okay, so you see that 11 is a big issue. On the other hand, if you go to the previous 50, already you will see it's much better even for this kind of confidence. So you can see the same sort of calculation here. So if you had to do 1 minus sigma squared by 50, sigma squared is greater than 0.95. Again, you would get the same sort of calculation. This implies delta squared is greater than sigma squared by 50 times 0.05. Notice again you get a square root of, so delta is greater than square root of 2 by 5 sigma. Look at this. This goes less than sigma, right? Even for 95% confidence, you can put with quite a small delta. Okay, so sigma is like, I don't know, 0.3 or something. Then you really get a very small delta, and you can have 95% confidence about that delta. Okay, even with the bound as weak as the Chebyshev bound. But look at how large you wanted to go with delta before you can have some sort of a confidence of sample mean lying within a large enough interval. Okay, so think of this example, and this sort of brings out why number of samples is very important, right? At least assuming you're in the IID samples domain, assuming things are okay, you notice how much more easy it is to work with 50 samples as opposed to 11 samples. 11 samples to get 95% confidence, you have a huge window that you need, right? From 40 to 80 or something. That window you can have 90%, 95% confidence. But with 50 samples, you're getting a much smaller window. Root of 2 by 5 is quite small, times whatever sigma is, right? So whatever the sigma is in that problem, you get that. Okay, so it seems fine enough. So the numbers are quite important. Here is runs scored in delivery 0.3 and n is 1598. Okay, sample mean is 0.9524, and you can be really confident about it. If you want 95% confidence, what would be delta, and you'll get a very small delta, and you can really be quite confident about where your sample mean is. Okay, so but still all this is hinging on some assumption. Okay, so this is actual data, and you have to assume IID samples type of model. You have to justify that in some way, or at least intuitively it should make sense to you. And next is the value of sigma squared. Even that you have to sort of estimate from the data that's available. You can do that, but nevertheless, when number of samples increases, your confidence level seems to be quite okay, right? So you're able to predict that the sample mean is reasonably within a small interval of the distribution mean. Okay, so hopefully this gave you a sense of where we are heading with this kind of an analysis. We are deriving statistics from samples, but we're not stopping there. We are trying to assess as to how good our statistics are, how well we predict distribution properties from the statistics that we collect from the samples. Okay, so what are the kind of calculations involved? Hopefully this lecture gave you a reasonable idea of how to go about doing it. We will come back to this. This kind of thing is called a confidence interval. We will study this in much more detail later, but even now you can already see where we are sort of headed in terms of the statistical study of phenomena. Okay, thank you very much. I'll see you in the next lecture.